Let's continue looking at limits. Most specifically, let's look at the limits of fractions. What we want to be able to do is to evaluate those limits algebraically instead of having to come up with a table or a graph every single time. Now, there's already a lot that we know about fractions and taking their limits. For instance, the limit as x approaches 3 of 1/4. Since 1/4 is a constant, the limit as x approaches anything of 1/4 is going to be 1/4. And for the limit as x approaches 3 of 1/4x, the only thing we really got to worry about with a fraction is that denominator being 0, and 3 is not going to make the denominator equal 0. That means that we can just directly substitute 3 into our fraction and get a limit of 1/12. In general, when we're dealing with the fraction like the reciprocal function 1/x, we know quite a few limits about it. For instance, the limit as x approaches 0 of 1/x. We know that if we approach 0 from the left, we expect negative infinity, and if we approach 0 from the right, we expect positive infinity. That means that the limit as x approaches 0 does not exist. And as we continue out towards positive or negative infinity, so going all the way out to the right or all the way out to the left, then we're always approaching that horizontal asymptote, and we'll end up with a limit of 0. For any other values of n, as long as it's not 0, it's not out infinity, then we're dealing with a nice smooth curve, and we could just use direct substitution and plug n in for x. But there are a couple other important things to notice. Here we're looking at the limit as x approaches 2 of x squared minus 4 over x minus 2. And initially we're looking at that denominator like we should, and we say, well, the only thing that's going to make the denominator 0 is 2. And I'm trying to take the limit as x approaches 2. So initially I'm thinking, man, this thing's gonna be does not exist. However, take a closer look. When we look at our numerator, x squared minus 4, we know that that is factorable into x plus 2 and x minus 2. We still have x minus 2 in the denominator. Since we have a common factor in the numerator and denominator of this x minus 2, they're going to cancel each other out. And we'll be left with the limit as x approaches 2 of x plus 2. Now, the thing is, when we did this canceling, it looks like we changed the function, but we really didn't. Okay? What we did is we simplified it so that we could get a good idea of what this function looks like. It looks like y equals x plus 2. So y-intercept of 2, slope of 1, it looks like this everywhere in its domain. However, going back to the original part, 2 is not in its domain. So if we're out here at 2, there's actually going to be a hole in our line. Everywhere else, it looks like the line y equals x plus 2. Then, the other thing to remember about limits is that we never get there. All right? The limit is our expectation as x approaches 2. Whether we're coming at 2 from the left or from the right, what do we expect that value to be? Not actually what the value is, because this function is not defined at x equals 2. But we have this expectation that we're going to follow the line to the spot where the y value is going to be 2 plus 2, or 4. We're expecting to get to 4. And this is really our big idea, that when we're trying to take the limit of a fraction and we see that we're going someplace that's going to make the denominator equal 0, don't just jump to that conclusion of does not exist. We maybe get some factors to cancel. Let's check out this one. The limit as x approaches negative 5 of x squared plus 3x minus 10 over x plus 5. Take a look at the denominator, x plus 5. The only thing that's going to make that thing equal 0 is going to be negative 5, which happens to be where we're going. Don't jump to the conclusion that our limit is going to not exist. What we should do is see if we can factor that numerator first, which obviously we can. Then we rewrite our limit as the limit as x approaches negative 5. We still have x plus 5 in the denominator, but when we factor the numerator, we'll have x plus 5 and x minus 2. Obviously, the common factors of x plus 5 are going to cancel, and the limit of this fraction is going to have the same value as the limit as x approaches negative 5 of x minus 2. So this is no longer a fraction. Now it's a nice linear function, so we could use direct substitution and get a value of negative 7. Oh, one last thing that I do want to point out, very important as far as AP goes and how we're supposed to be expressing and communicating mathematics accurately and writing down logical statements. As you are simplifying a limit, always write this limit part until you actually put that value in. Until you do that direct substitution, until you're actually evaluating the limit, you have to write limit in front of your expression. Let's try another type of polynomial that we're familiar with, the difference of 2 cubes. Here we're looking at the limit as x approaches 4 of x cubed minus 64 over x minus 4. Obviously, this 4 is going to make our denominator equal to 0, so we have to be worried. Factor the numerator. Obviously, keep the limit around, like I said. We're not taking the limit yet. What we're doing right now is just factoring it. Keeping that x minus 4 in the denominator. When I factor the difference of 2 cubes, I have a short factor and a long factor. My short factor is the cubed root of each term, so x minus 4. And for the long factor, we have 3 terms, which I always remind myself as square together square. And we go back to our short factor, and I'm going to square that x as x squared. Then I put the x and the 4 together as 4x. Now this term has to have the opposite sign as that minus, so it's going to be plus. And then we square the last one, square together square. So that's going to make 16, and the square is always positive. Now, of course, we got some canceling that can happen, common factor of x plus or x minus 4, and we can rewrite our limit. So we'll have the same value as the limit as x approaches 4 of x squared plus 4x plus 16, a nice polynomial. Now I'm going to evaluate the limit using direct substitution, and we'll have 4 squared plus 4 times 4 plus 16. And that looks like 16 plus 16 plus 16, or 48. Let's generalize that just a little bit. I do want to get you used to having x minus a in the denominator. But we still have the difference of 2 cubes in the numerator, so I get to rewrite my limit as x approaches a. We'll have x minus a in the denominator, and the difference of 2 cubes, short factor, long factor. The short factor is x minus a. The long factor, we square together square. So square the x, opposite sign in the middle, then put the x and the a together, and square the a. Now we'll have our common factors cancel. Rewrite the limit as x approaches a, of x squared plus ax plus a squared. And when we substitute a, then we are evaluating the limit. We don't have to write limit again. So we substitute a for all the x's, and we'll have a squared plus a times a plus a squared. And we get 3a squares. So look for things to cancel and then evaluate the limit. And maybe we can come up with a value instead of just writing dne.